The Union Pacific Big Boy is the most famous steam locomotive ever built. 138,000 pounds of starting tractive effort, the very definition of power on rails. But in 1941, Baldwin Locomotive Works delivered a single engine to a small Appalachian coal railroad, generating 229,000 pounds of pull. By some measures, enough to rival two big boys working in tandem. Yet this locomotive was nearly erased from history. To understand how something that powerful could simply vanish, you have to start with the one machine everyone remembers. Union Pacific's Big Boy didn't just set a record, it defined the upper boundary of what a steam locomotive could be. Designed by the railroad's Department of Research and Mechanical Standards, the Big Boy's numbers still command respect among engineers and enthusiasts. Its starting tractive effort reached 138,240 pounds force, a figure calculated at 85% of its 300 pounds per square inch boiler pressure. That's not just a statistic. It's the raw force needed to move a fully loaded freight train from a dead stop up the steepest grades the Wasatch Mountains could offer. The Big Boy's frame carried a wheel arrangement known as 4884. With 4 leading wheels to guide it into curves, 2 sets of 8 driving wheels to grip the rails, and 4 trailing wheels to support its massive firebox. Each of those 16 drivers distributed the locomotive's enormous adhesive weight, 720,000 pounds, across the rails, keeping all that power from turning into a useless wheel slip. The entire machine, without its tender, tipped the scales at nearly 1.2 million pounds. Coupled to its tender, the total weight approached 1.8 million. In practical terms, that meant a single Big Boy could haul about 3,600 tons of freight up a 1.14% grade, a stretch of track notorious for breaking lesser engines. The continuous tractive effort, measured during dynamometer car tests, hovered around 120,000 pounds force at speed. In a 1942 test run between Ogden and Wasatch, the Big Boy managed a 3,600-ton train unassisted, confirming the engineering team's predictions. The Big Boy's design wasn't just about brute force. Its articulated frame allowed it to navigate curves that would have been impossible for a rigid locomotive of similar size. The massive 68-inch drivers balanced speed and torque, while the 300 pounds per square inch boiler and 424 by 32-inch cylinders delivered the sustained power needed for long, mountainous hauls. The firebox alone covered nearly 180 square feet, large enough to swallow smaller locomotives whole. Every figure from the original Department of Research and Mechanical Standards reports 138,240 pounds force tractive effort, 720,000 pounds on the drivers, and the 4884 wheel arrangement became the standard by which every other steam locomotive would be measured. In the world of heavy freight, these numbers weren't just impressive. They were the boundary between what was possible and what was merely legend. Baldwin Locomotive Works, already famed for building giants, took on a commission in 1941 that would stretch even its own definition of power. The order came from the Virginian Railway, a coal hauling line that faced a relentless enemy, the steep, twisting grades of the Appalachian Mountains. Board minutes from that year, preserved in the railroad archives, record a bold directive: build a locomotive that could conquer the giant grade with a single engine, eliminating the need for double heading or helper sets. The result became known as the Virginian 210-10-2, Class X, serial number 5392, road number V 2300. Chief Mechanical Engineer J. H. Thomas of the Virginian spelled out the requirements in correspondence with Baldwin's superintendent. The engine needed to move 4,000 tons of coal up a 1.6% grade. No small feat when most mainline locomotives struggled with half that load. Baldwin engineers responded with an articulated mallet design, 10 driving wheels on each of 2 sets, preceded by a pair of pilot wheels and followed by two trailing wheels to support the immense firebox. The locomotive's physical presence was matched by its numbers. At 229,500 pounds force of starting tractive effort, V2300 had raw pulling power that eclipsed any other single steam locomotive in North America. Its adhesive weight reached 840,000 pounds, spread across 20 drivers to maximize grip on the rails. The entire machine, coupled to its tender, tipped the scales at 1.3 million pounds. The procurement chain behind V2300 involved more than technical ambition. The Virginian board, led by Vice President and General Manager C.C.P. Miller, saw the locomotive as a solution to a very real economic bottleneck. Every stalled coal train on the giant grade meant lost revenue and cascading delays at the port. The board minutes reveal urgency. The new engine had to be delivered quickly, tested under full load, and deployed in regular service before the next winter surge in coal demand. Baldwin shop order archived as serial number 5392 captures the technical dialogue, specifications for boiler pressure, cylinder dimensions, and even the minimum turntable length required for the locomotive's enormous frame. With V2300, the Virginian Railway set out to redefine what a single locomotive could accomplish. Yet the story of this machine is not just about numbers or scale. It is about the people who signed off on its creation, the engineers who designed it, and the crews who would soon put its power to the test. The next chapter would reveal whether this unprecedented force could solve the railroad's toughest problem, or whether power alone was enough to guarantee a place in history. The stretch of track that haunted Virginian railway planners wasn't just steep, it was relentless. The giant grade, as it was known in the company's engineering memos, climbed at a punishing 1.6% for miles, winding through the Appalachian backbone. On paper, that number might seem modest. In practice, it was a wall. Every loaded coal train faced a simple equation: either split the tonnage and double-head two engines, or find a way to move 4,000 tons up the incline with a single locomotive. Each additional engine meant another crew, more fuel, and more time lost as trains were broken up and reassembled at helper stations. The cost lines in the Virginian's annual reports spelled it out. Double-heading on the giant grade was eating into margins, turning what should have been the railroad's most profitable run into its biggest operational headache. For the planners, the stakes went beyond dollars and timetables. The giant grade was the artery through which the region's coal reached the coast. Any delay there rippled outward, slowing shipments, tying up rolling stock, and threatening the railroad's reputation with its largest customers. The board's internal correspondence from 1941 lists the numbers in stark terms: a 4,000-ton train, one engine, up 1.6%. That became the target, no matter how extreme the specifications required. The challenge wasn't just about brute force. It was about breaking free from the cycle of helper engines and bottlenecks that had defined mountain railroading since the first rails were laid. Solving this problem demanded more than incremental improvements. It called for a leap in design, a machine that could anchor the entire operation. The planners didn't just want a locomotive. They needed a solution to the grade itself, something that would let them run heavier, faster, and with fewer interruptions. Every engineering memo, every calculation, circled back to that single, stubborn stretch of track. The giant grade dictated the rules, and in 1941, the Virginians' leadership decided it was time to change the game. The specifications that followed would push the limits of steam power, all in pursuit of a solution to the mountain bottleneck that had long defined the railroad's fortunes. Baldwin's answer to the Virginians' mountain problem was a machine defined by excess, a locomotive whose statistics read more like a dare than a blueprint. The construction sheet for V2300, archived as Baldwin serial number 5392, lays out the numbers with clinical precision. The starting tractive effort was 229,500 pounds force. That figure alone eclipsed anything else running on American rails, and it was not theoretical. Baldwin's own dynamometer car confirmed the measurement during factory acceptance trials in late 1941, with the locomotive delivering its peak pull at just over 10 miles per hour. The heart of this power lay in a 260 pounds per square inch boiler, feeding steam to 4 massive 24 by 30-inch cylinders, 2 for each engine set. Each stroke sent a surge of force through 20 coupled driving wheels, their 57-inch diameter chosen to maximize grip instead of speed. The adhesive weight pressed onto those drivers reached 840,000 pounds, nearly 120,000 pounds more than the big boy. With so much mass on the rails, V2300 could claw its way up grades that left other locomotives stalled and gasping. But the scale did not stop at weight and pressure. The locomotive's articulated frame stretched over 100 feet, demanding new turntables and pushing the limits of the Virginian's existing infrastructure. Baldwin's engineers specified a bearing overhaul interval of just 12,000 miles, about half that of the big boy. Because the rear engine's journal boxes ran so hot under load, shop records show that every month the locomotive would spend days in the roundhouse for bearing replacement and inspection, a maintenance cycle that became as much a part of its story as its record-setting pull. Every element of V2300's design was a response to a single problem: how to move 4,000 tons of coal up a 1.6% grade without help. The result was a machine that on paper could outmuscle any rival. Yet the same numbers that made it a marvel on the test track would soon reveal the limits of brute force in the real world. The next step was to see how all this engineering translated into day-to-day performance, and whether the most extreme specifications ever built could actually deliver on their promise. Freight planners at the Virginian Railway laid out their challenge in stark, unambiguous terms: move 4,000 tons of coal up the giant grade with a single locomotive. This figure wasn't from a marketing brochure or an engineer's daydream. It was set down in a planning memo dated October 1941, signed by the board and circulated through the railroad's operating divisions. The number wasn't a guess. It represented the full length of a loaded coal train, the tonnage that kept the port terminals humming, and the company's balance sheet in the black. Every operational decision, from crew assignments to fueling schedules to track maintenance, revolved around that target. On paper, the 4,000-ton goal was more than just an engineering milestone. It was a direct response to the bottlenecks created by doubleheading. Each time 2 engines were lashed together to climb the grade, costs multiplied. More crews, more fuel, more delays as trains were broken up and reassembled. The planners knew that every extra locomotive on the giant grade meant another point of failure, another opportunity for schedules to slip and profits to erode. The 4,000-ton figure became the yardstick by which every new design was measured. It appeared in freight forecasts, in procurement contracts, even in the minutes of board meetings. The railroad's engineering staff translated it into specifications: tractive effort, adhesive weight, cylinder size. But the core demand never changed. 1 engine, 1 train, 1 mountain. Success would mean fewer helpers, faster turnarounds, and a leaner operation. Failure would mean more of the same: congestion, overtime, and a constant struggle to keep pace with demand. As the locomotive neared completion, the stakes attached to that number only grew. The planners weren't just chasing a technical record, they were betting on a machine to break a cycle that had defined mountain railroading for decades. The 4,000-ton target wasn't just a figure in a memo. It was the promise of a new era, waiting to be tested against steel rails and Appalachian grades. Baldwin's test engineers set up the dynamometer car behind V2300 on a crisp November morning in 1941. The goal was simple: measure in black and white what this locomotive could actually deliver. The first run, conducted on a straight stretch of factory track, registered a peak tractive effort of 235,000 pounds force, more than any steam engine in American history. That number was not a fluke. The test log, signed by both Baldwin and Virginian officials, records a sustained draw of 210,000 pounds force at 10 miles per hour, with the boiler holding steady at 260 pounds per square inch. Every gauge, every dial, seemed to confirm the machine's promise on paper. But numbers from the test track only tell part of the story. In the hills of Appalachia, where the giant grade punished every weak link, the real test began. Crew records from 1942 and 1943 show V2300 regularly assigned to the heaviest coal trains on the division. On March 18, 1944, the locomotive hauled a 4,500-ton consist up a 1.2% grade, a record documented in the engineer's logbook and later cited in the railroad's annual report. The run took just under 8 hours, with the locomotive maintaining a steady 8 miles per hour for the steepest sections. Firemen recalled the relentless demand for coal, shoveling over 5,000 pounds an hour to keep the boiler at pressure. The engine's dual air brakes, tested to their limits, kept the descent controlled when the summit was finally reached. Maintenance logs reveal the cost of this performance. Bearings on the rear engine set required overhauls every 12,000 miles, and the locomotive often spent days in the roundhouse after a particularly heavy haul. Yet, in terms of raw output, the numbers held 235,000 pounds force at peak, 210,000 sustained, and a 4,500-ton train moved in one piece. These figures were not just theoretical. They were witnessed, logged, and signed off by the men who ran and maintained the machine. The results would soon face direct comparison with the legends of steam, but in the moment, the evidence was undeniable. V2300 could deliver more force and move more weight than any other single locomotive of its era. Comparing raw numbers, the myth stands on a razor's edge. Two Union Pacific big boys combined produce a starting tractive effort of 276,480 pounds force. That is the absolute ceiling of American steam, at least in the public imagination. But when the numbers are lined up, the Virginian 210-10-2 comes close enough to blur the line between legend and reality. Its peak tractive effort, verified by dynamometer car and factory trials, reached 229,500 pounds force. That is 83% of the two big boy benchmark, just 47,000 pounds short. For a single locomotive, that is a staggering figure, one that no other American engine ever matched in a single frame. But peak numbers only tell half the story. Sustained performance on the rails matters more than a fleeting burst. The Virginian's continuous tractive effort, the force it could hold, mile after mile, grade after grade, clocked in at 210,000 pounds force. That is about 70% of the combined output of two big boys, whose own continuous effort, doubled, would reach roughly 240,000 pounds. In practical terms, the Virginian 210-10-2 could haul around 5,000 tons up a 1% grade, while two big boys together could move closer to 7,200 tons. The gap is significant, but the scale remains almost unthinkable for a single machine. There is another limit that cannot be ignored. Brakes and couplers set the ceiling for what any locomotive can safely move, no matter how much force it can generate. Standard Westinghouse air brakes, rated for around 2,400 tons per locomotive, often dictated the real-world maximum. Even the most powerful engine cannot outrun the physics of steel and air. The Virginian's immense power sometimes exceeded what the infrastructure could safely handle, forcing operational limits well below the theoretical maximum. So the verdict is clear. No steam locomotive in the historical record ever surpassed the combined force of two big boys. The Virginian 210-2 came closer than any other, but the claim does not stand up to the numbers. In the end, the story is not about shattering records, but about how close human ambition came to the edge of what rails and steel could bear. And it leaves a lingering question. If power alone is not enough, what really decides which giants are remembered and which are forgotten? Today, the big boy stands in museums, while Virginian number 164 is just a footnote, despite its unmatched hauling power, documented at more than 260,000 pounds of tractive effort. In a world chasing records, it's not brute force, but adaptability, myth-making, and memory that decide what endures. The ultimate legacy isn't written in tons moved, but in the stories we choose to remember. What do you think survives? Power or presence?